still have enough time for the discussion, hopefully. So my name is Anastasia. I'm a historian of art, science, and technology, the doctoral student here. And today we'll have among participants David Rosenboom, musician, scientist, the way he called himself in early 70s. Mattia, co-director of the research group Vitro, Hamilton, Dean of the College of Fine and Applied Arts, and also Sever, the very research assistant of Mattia's lab, who will be participating in the discussion. So the overall plan for today is to start with the brief presentation of David, then we'll pass to Mattia, then we will have some musical interpretations of neural activity played, the brand new sound samples, and finally we will have the discussion, which probably will take most of the time altogether. So perhaps briefly about Vitro, the brand new group pursues creative exploration, blending art and science, exploring how groups of neurons compute. They intend to build plastic cellular substrates, build up living neurons, and David is well known for his half-century-long history of work with using neuron responses for making art. So today we will share the results of the very recent interpretation of recordings provided by the group Vitro in their sonic form. That's it. Let's get started.
Thank you.
Thank you.
Thank you, Anastasia. So I'm going to start by just giving a little background of my work, and then Mattia will take over and talk about the Mind in Vitro project, and then we'll go to the demo. So, and then discussion. So, so these are just a few slides. I'm not going to do that, actually. I'm going to just talk about one piece, and I apologize for anyone, I know one person in the room has seen this before, but it's a good thing to give a background. So I started working with what I might refer to as neuromusic, or extended musical interface with the human nervous system, or biofeedback and music and the arts in around 1969, 1970, and have worked with it off and on since that time. I worked with it very intensively through the 70s and into the 80s. Then there was a kind of a lull for a while. And then later on, and in more recent time, there have been huge advances in the technology involved, the accessibility of the technology, the cost of the technology to get very good recordings of EEG signals, and to analyze them, and the theoretical techniques of signal processing and so on got much more sophisticated. So, so now I'm back in it again, and this is and it's become a huge field. So, and so I'm just going to describe this one piece that I did recently with collaborators from the Schwartz Center for Computational Neuroscience at UCSD in California, in San Diego. And this one involves the idea of a notion of what we call the hyperbrain, using a hyperscanning technique. So it's a work in which we have 4 individuals who are participating in a performance wearing multi-channel EEG headsets, and they are treated as one big brain. So we are looking at the responses of this group brain, as you might think of it that way. And then we are also recording what are called event-related potentials, which I'll show you what that means in a minute. So this was our first go of the piece in 2014 in San Diego. And what you see here are my little red dot shows you there are 4 people here with headsets. They're sending data to my colleague Tim Mullen, who is running a program to detect what we call principal oscillation patterns, which are the emergence of what might become a resonant phenomenon in the brain, a ringing effect among groups of neurons, and in this case across the four. He is sending me the results of that analysis in real time to my system, which is mapping that information onto a computer music instrument that I built for this process. And then two of us actually, eventually in the process, actually start playing with those brain performers. It's a process I call listening as performance. So we're actually, they're actually, there's a cybernetic process going on. This is a feedback loop, and they're learning to work with what emerges and investigate what happens when they listen in a different way or shift their attention to one thing or another. And so I've built it so a musical structure emerges. And then we start playing with them. So we become a band. So it's the four people with headsets and two of us playing with them. So this is a simplified diagram of the whole thing. These principal oscillation patterns are detected. They're going to a bank of resonators, a bank of digital resonators that are digital simulations of ringing circuits that have various sort of complex parameters that can be given to them to make them sound in different ways. And then sound is distributed in space. I won't spend time going into this. It's just a poster display of the research that Tim Mullen was involved in to develop the ways of detecting these principal oscillation patterns. It actually comes from work in studying epilepsy and finding ways to detect the emergence of these ringing phenomena in neural circuits before they spread through enough of the brain to actually trigger a seizure. So that's where that research began. And then this is just a display of over 0 to 40 hertz signals in the EEG, looking for the emergence of what might be these ringing patterns, which are these circles here in that pattern. This is the user interface for my bank of resonator circuits, which is created in a program called Reactor. It's a very complex program in its interior structure, and then this shows the mapping of the information that happens. An index number indicating which principal oscillation component we're talking about, what its frequency is, what its damping time is. In other words, how long does it ring? Its excitation level, whether it's an oscillator or a relaxator, what its frequency stability is, that's important. Whether it's a fixed, very solid frequency, which is not a good thing for the person's brain, but we can usually there's some variation, and then its dispersion across the group of four. And that's mapped onto the parameters of this this computer music instrument. It's documented in this book. I mean, that chart I just showed you is in this book from Springer. And this one I just wanted to show people because since I started with this now back in about 1970, there were not too many of us working in this area. I published a book in 75-ish called Biofeedback in the Arts, which has now come back to be something people want again, and surveying what had been done in the field. And now this has turned into a huge field. BCI in the arts, brain-computer interfaces in the arts, has become a huge field with international gatherings and even festivals at this point. So here's the close-up picture of the four people. They're wearing headsets made by a company called Cognionics, multi-channel headsets that transmit EEG over Wi-Fi. And this is a picture of the 2015 version of the piece that was done at the New Whitney Museum of American Art in New York, when they opened that new building. I was I was really honored that they chose to do a 4-event retrospective of my work to open their new performance space. So in this case, there's also a visual display. We think of these resonant patterns as like dropping a stone in a pond and the waves spread out. And we kind of visualize that by mapping the frequency of the signals on the up and down part of the screen, the dispersion of energy across the 4 people across the horizontal part of the screen. And then these would be like light splashes that go in on the wall. The brightness and color and spread, how fast they spread, relate to the other parameters of the principal oscillation component being detected, its stability, its amplitude, and so on. And there's another picture of it. There's some sound from, as these oscillations, these pops as we call them, are mapped into the computer music instrument. If this loads, we'll see, it looks like it will. This is now you can see the visual stuff. This is just a few excerpts from a performance at the Whitney. I'm playing with them, and the event-related potentials are being played on a piano, on a computer interface piano. I'm going to move it ahead because we got a late start. Just let it come to me. And that was the end of the performance. Okay, so I asked, and when I learned about what the Mind in Vitro project was about, it led me to thinking about how do we assign meaning to what we are recording from these groups of neurons in your culture? So maybe that'll be part of our discussion. And ways in which communication has to be co-creative, by reflecting things back and forth, or emanating original things and sending, or by affecting mutual interactions, like language might emerge. So that's a sort of a pie-in-the-sky projection into the future, questions we might ask about this. And I'm going to come back to that and stop that one and turn it over to Mattia.
Thank you.
Now you need the HDMI. Can I just pull it and switch it?
Yeah. Okay. I just need the HDMI.
Oops, sorry. You got it? Oh, you don't need the adapter. Okay. It takes a minute usually. Yeah, there you go.
Can I stand? Yeah. Hello, can you hear me? All right. Okay, hi everyone. So I am Mattia Gazzola from the Mechanical Science and Engineering Department. I'm an assistant professor over there. And today I'm gonna give you a little bit of an overview of our Mind in Vitro center and how some of the work that we do connects to music and arts. So this is this Mind in Vitro is an NSF expedition, which is a center-scale program from the computing department that, you know, every few years awards a big group of people, you know, some resources, significant resources to kind of pursue a very bold type of, you know, ideas. And what we have been proposing or thinking about is really how do we build and compute with neurons, all right? So before jumping into what we do and how we think of doing, this is who we are. So that's myself. I'm one of the 3 co-directors. Nancy Amato and Taher Saif are the other 2. We have thrust leaders, Jun Kong, Karin Damen, Joseph Torrellas, Lawrence. And then we have experts across different domains, from psychology, information theory, bioengineering, assessment, ethics, biology, neuroscience, microfabrication, and electronics of all sorts. So in these expeditions, basically, we have imagined to, you know, how we might be able to build computing systems and robotic systems that are living, but at the same time, and they're engineered by us, but at the same time can be programmed, or that can, you know, that possess a structure or a certain set of behaviors that, you know, allow them to explore, adapt, and interact among themselves and the environment. And so here is 2 examples of one of our platforms in which we grow some 3D neural tissue, and this is a tiny swimmer that is able to sense some light and swims towards it. So the entire project basically revolves around this idea of developing a computing stack, much like computers are developed today, but now centers on the use of cellular substrates. And the reason why cellular substrates might be a good idea, and I'll come back to that in a minute, is because they have this ability to generate dynamics that emerge spontaneously and then evolve in time. And we think that this is the key to access some of these traits of intelligence that are difficult to, you know, achieve with nowadays artificial intelligence. And we would like also to show some of these abilities within biological robots that can move around and perform tasks that perhaps are useful to us. So here's an example of the little stingray that I showed you before. As you can see, every time the light is shown, it flaps its fins, and if you increase the pace of excitation, this little swimmer starts moving around and chasing the light. So why is it interesting to think about computing in terms of neural substrates? I mean, we have perfectly good machines today to compute. So why bothering to move into a completely radically different type of environment? So there are many reasons why this could be a good idea. I'm just going to point out a couple of them just for context. So some of them are practical and some of them are really related to algorithmic ability that we do not possess today. So this is an example. I don't know if you are aware of how expensive it is to train a deep learning neural network nowadays. So what you see here is the following. Each one of these dots is the best deep learning algorithm in the world at the time when tested onto this set of images, and testing the ability of this algorithm to recognize objects, for example, a dog or a cat or any type of image within this data set, okay? And here is the percentage of error, and here is how much it costs in terms of energy translated to carbon dioxide emissions, okay? So here, for example, in 2012, the best algorithm in the world made had a 30% error rate and produced some tens of pounds of CO2, okay? And now here, in 2020, we lowered the error to 10%, which is still pretty high compared to what we can do. But now, to train that neural network, you produce more CO2 than an average US person in the year in the US over 1 year, and almost the amount of CO2 that an average person produces over his entire or her entire lifetime. And if you project linearly, the moment will hit 5%, which is still pretty high, 5% error in recognizing images, that the amount of CO2 that you would need to pump into the atmosphere to train that network is about what is produced by New York in a month. So there is really a big bottleneck in terms of the energy that is necessary to train these systems that we use all over the place. And so, how do we go from there? And if we think of it in terms of our own capabilities, well, our brain consumes only 20 watts, and we are much better than these systems that recognize images. So so neurons or cellular substrate are very efficient in terms of energy. So that's a very appealing quality. But there are other interesting properties. So for example, nowadays we build chips, and these are mostly 2D, and the connection between transistors are laid out in a plane, and that gives you a certain level of connectivity, but neurons connect in 3D. And each neuron can have up to 10,000 synapses each. So the level of connectivity is really absolutely extreme, and that gives you a lot of compute power in a very tiny space. But I think perhaps the most interesting aspect of these systems is their potential in terms of algorithmic abilities. So here I'm going to play these 3 cartoon simulations just to give you a sense. So if you have a network with very sparse connections, okay, when you see the electric activity of this network, you just see these kind of small dots. That means that you can encode just a little bit of information somewhere locally there, okay? If you have too many connections, then, well, your network is just on and off. And also there, no processing abilities, just either on or off. Okay, but neurons have this capability of self-tune on their own without us doing anything around this very, very special place in which you have enough sparsity and enough connectivity so that a very vast number of dynamic patterns can be generated and created on their own, on the fly, okay? And you can demonstrate that around this condition is where complexity emerges and new patterns and new dynamics emerge. And so we think of these as really key, the key property that might allow us to, devise machines that are able to truly learn to perform these, cognitive operations such as association, creativity, curiosity that really are missing nowadays in AI. All right, so how do we want to do it? I'm just going to, very briefly give you an overview. So our program is structured in different thrusts. One deals with creating the hardware that we call wetware because it's biological. So you need to be able to interface with these cellular substrates, grow them, maintain them so that they're healthy, read out, read in, and make sense of their signals. Once you're able to create units of these neural cultures, you might start thinking exactly how we do in computers to connect different units that have different properties into more powerful architecture, so to augment the computing capabilities of the system. And then, of course, you need to make sense of all of it. And so you need, and here this is a machine very different from our laptops where we apply finite state machine, which is very successful computing model, but we cannot use it here because these systems are so dynamics, they make a lot of mistakes, they're noisy. So we need to think of a new math, of a new computing paradigm to make sense of this system and use dynamics rather than bits to carry out computations. And finally, we want to embody all of this in a tiny robot so that this robot can perform some useful functions for us. There is also a number of other aspects related to this project, but one is a connection with art and science, and here is the reason why we love to interact with you. All right, so now I'm just going to show you a few pictures to give you a sense of how our system look like. So here's one of our recording devices. Also, let me say that the person that is behind all of this development is that guy over there. So he is the one that has been developing most of it. So what you see here is basically down here, very tiny, there are some neurons, okay, that sit on a bed of very small electrodes, and we can stimulate these neurons through lights, through electric system, and read out their dynamics, and then make sense of them downstream. And so, of course, to make sense of them and compute, we need to develop software and models to be able to do that. I'm not going to go into this today. But a big focus of our entire work is really to develop open hardware that is very accessible broadly and open software. And so here is how our hardware looks like. That's another version. And we want to build something that is better than commercial devices. There are some commercial devices that do some reading that are used typically in drug screening, and from people that really don't care how expensive they are, and they are outrageously expensive. And so this prevents anyone else to use them. And so we want to really lower the barrier entry here. And so here, all of this is made of inexpensive materials and solutions. This one is an Amazon latch for $1, for example. This is a hinge also from Amazon, $1, okay? So, and the neuron sits here in these tiny wells. We can pump in fluids to keep them happy, read out their signal. They are rerouted through this PCB board, and then they come out of here, the amplifier, preamplifier, and then they go into our system. We can access them from top and bottom, stimulate them in different ways, and make sense of them. Yes, so here's the overall system. It's very low profile. This is how it looks. It's pretty small. That's a tiny mini incubator, a couple of $100. The electronic acquisition box that feeds everything into your laptop, and then you have an interface with these systems. And yeah, again, so if you go and compare with very, very basic commercial system, the reduction in price is dramatic. So here is where really all the magic in the end happens. So this is basically the layer through which we read out or we stimulate the neurons. And these are all these tiny cables or tiny connections that help to bring out the signal eventually to your computer. But all the neurons sit somewhere in this very, very tiny space. And you can see here these tiny dots are those electrodes that measure the neural activity. And we have tested this system, and we routinely perform different type of tests with different type of cells, stem cells derived, primary neurons, and even brain slices. So this is a slice from a mice that is put on there, and we can record and stimulate from it. All right, so this is just to give you an idea of how this system may look like. And this is, a zoom in of what is happening here. The neurons are here, and this is a raster. Each dot here is a spike of a neuron, and you can see that there are sometimes these bands when the neurons synchronize, and then they have their own activity. We can zoom in and see the shape of their activity and tell something useful out of it. For some reason, this is not working well. Oh, yeah. And so, and the other component is really to bring all of these on board of biological robots. So this is a tiny walker, and this kind of jello stuff here is muscular tissue that is anchored to this pillar. There are two of them, and if they contract, this thing walks or maneuver in different directions. We can now have more sophisticated versions in which we directly integrate an electronic chip within the muscular infrastructure. We can control this chip remotely and get these robots to walk around. And so now here, also from the body perspective, we have the infrastructure to allow us to start thinking about plugging in directly neurons in here and control their communication with the muscular infrastructure, so that you can imagine that these tiny robots can sense their environment, make decisions, and decide what to do on the fly. All right, so now going back to David and Seung, here is how this connects to music. So obviously, one important thing, if you think about adaptivity, is the ability to sense your environment. So we are working towards developing an in vitro auditory system so that we can route sounds within our neural cultures, and then use the dynamics of these cultures to elaborate these sounds and synthesize new sounds, okay, in a way that is interactive. And so this is really what we are planning to do. Imagine that you play some sound. We are going to use cochlear implants technology to basically route sound directly into our neural cultures. These cultures, they're going to respond, generate their own dynamics, and we're going to feed this dynamic back into a synthesizer that is going to produce some music. And this way, we have a feedback loop between music and listening. And we can use this framework to explore the creative abilities of these systems. And David, of course, is going to help us with this, and is a perfect match for this type of for this type of work. Thank you.
Okay. Yeah. Can I switch? You can put it back there. I have to operate the computer. So, is it okay to take the HDMI? Okay.
Thank you.
We're going to switch the screen. Now the screen has to adapt. Yay, there it is. Okay, so here is something that we developed. This thing is really developed during my residency here. So working with Jung, in particular, sitting in coffee shops trying to make neurons make sound. And it was great to work together. And so here, this is a demonstration. I consider this this is like baby steps of what we might be able to do, but it's pretty cool. So what we have here, I'm going to play you 2 recordings that Seung provided of neural spikes. And what I have done is, you can see my cursor there. So I have mapped these. There's a module up here, which is just a display of the values of each of 36 channels of neural spike information coming in. So when I play it, you'll see these numbers flashing around. And then these devices, there are actually 3 of them. Each one processes 12 channels of the spike data and essentially generates a trigger that will bing a sound, will actually activate one of these resonators that like I used in that other piece, but I've adapted them for this process. And they are shown down here. And then this is just a mixer bringing it up, so it's up, and we were having a little trouble with getting into the sound system, so you're going to hear them over the computer speakers that are being mic'd. But so the first one that is up here is a recording of spontaneous firing. I would describe it that way. And then I'm going to play you another one where they're actually being stimulated by light. So you can watch it, and let's see what we get. Takes a second to load. So you can see these are the channels. It's first 12, the next 12. You can see the numbers flashing here. And this 12. There you can see all 36 channels. Some of them are active, some of them are not so active. And you can hear what they're doing. Okay, so that was that recording. Now I'm going to select another recording, and this one is the one in which the neurons are being stimulated by light flashes, if I understand it correctly. Okay. And I've just changed my preset here. Okay. Here we go. It's loading. You can probably hear they're a little more active. And you can see it too. So that's the stimulated recording of the neurons that are stimulated. Whoops, it's playing again. I think my trackpad is a little too sensitive. But I'll tell you what, actually, since it's playing, this just for fun, each channel is in what you're hearing now is assigned to a particular resonator that has a pitch, and those pitches are spread over approximately the range of a piano. 36 of them just sort of evenly spread across that range. Just for fun, I use something to modulate the scale that they're playing in, just to hear it change, and it's purely for musical fun. It's the same data we were listening to just earlier. There you have the concert. All right. So that's what we've done over just the past few days. So it's just a start.
Yeah, just for context. So this second recording is so we stimulate these cultures with light. So these are neurons that have been genetically modified, so they respond to certain wavelengths, and that's how we think about incorporating visual cues, so the sense of sight. While this work in particular is about bringing in this different sensory stream, the sense of sound instead, and beyond the music and the creative aspects of it, what also is very interesting for us scientifically is to study how different sensory streams might fuse together, how this can help enhancing some cognitive abilities, like the same way you read a word and you hear it, and if you do it at the same time, you remember it better. So how does that work? Nobody knows. And then one last thing I wanted to mention is that before I singled out Xiaotian for the hardware development, but Seung, he's the one that is pushing the software development, and he's been working with David in coffee shops these past few days to get this to work.
Right.
So thanks to both of you.
Yes. Yes. Great. Well, should we, Kevin, you want to join us? And we can speculate a little bit. I threw up some questions up there on the screen, which I shared with my colleagues, just that occurred to me as kind of interesting questions to discuss this, but discuss where this might go and what it might mean. But we can go anywhere in this discussion.
Yeah, I think we have something like from 30 to 40 minutes, and the good start of this discussion of artistic implications of neuronal discoveries, I think it would be a good start to give the third perspective on this whole collaborative effort. Yeah. Sure. So we will give the floor to our expert in the history of psychoanalysis.
Oh gosh. Well, I'm always glad to provide context for who I am as an interlocutor, which is what I want to be with you too. So first of all, thank you both for taking this on as a collaboration, and thank you, Anastasia, for these last 2 weeks. I'm going to keep my administrator hat on for a few more minutes, and then I'll take it off and try to be the scholar again. I've been here 21 years here at University of Illinois. I came here looking for a place to be an art professor. Came out of art school, community art, public art program. I came here more or less by way of MIT, where I was there not at the media lab, but in the architecture school, operating in the remnants of what used to be the Center for Advanced Visual Studies, which was a very important lab in the 60s and 70s. Right. And by the time I got there, it was a bit on sort of looking at the possibilities of taking a research-based approach to artistic interventions in public space aided by computation. So my faculty at that time were a kind of mix of real epistemologists of being in the kind of minimalist art context, and agitational techno avant-gardists like Krzysztof Wodiczko, a sort of Polish public artist. And so I came here making art, making interactive art, and really making a lot of telematic interactive art was kind of my background. So I've been long interested in these questions of both representation and community that happen when you set up these systems as you have, starting with one actor in a system and outputs, how you begin to understand what's happening there and how it's an extension of you or not. Then you add multiple actors and it gets more complicated. So I feel like I can jump in with you all in this kind of questions of representation, of agency, of ontology. What is the thing? What is the being in these things? But then again, with my administrator hat before I take it off, is I've been 5, 6, 7 years now in administrative role. I got interested enough in the research culture here, and I'm a student of history, that I began to wonder how I can help facilitate the improvement of the organization applying hopefully my civic art skills to organizational development, but with an artistic approach, hopefully. And I'm a big believer that we've got to work across the domains, as you all are doing, but also across history. And this is another thing I'm really grateful for about Anastasia's work here, is to make sure that we're operating across time here. So much of this kind of interdisciplinary work that happens is, you all probably know, it's fodder for the production of an interdisciplinary university in appearance, right? So it can so easily end with, we got a person from this part of campus to this part of campus together. They seem to have had some success. People seem to think it was good what they did. Aren't we interdisciplinary? Aren't we flexible? Without actually diving into these really important core questions that you all are so wonderfully bringing to us about what can we learn from our different approaches to what we believe to be thought, what we believe to be an event, what we believe to be agency. And so this is the kind of thing I hope we can get to more in an institution like this. So one more reference here to context for Anastasia. So I was here probably 6-7 years before I realized, ignorant that I was, that this was the Center for Cybernetic Research for decades.
Yeah.
And it was me watching a documentary that come across footage of Hans von Forster, the Austrian cyberneticist who came to teach in the electrical engineering department and created this very interesting thing called the Biological Computing Laboratory that got me down a rabbit hole of years of trying to learn about this work. Folks that this was a center, a really interesting place for interdisciplinary thought and research about these very issues y'all are bringing up, some of whom we've lost just recently. I think we just lost Klaus Krippendorf this week, who was a major communications scholar working in these questions about emergent order back in the day. So I get interested in these histories as well for reasons I said before, but I'm going to take off my minister hat and say I'm now here with you all thinking about Gray Walter's tortoises in light of this experiment, and really curious to hear what kind of differences you all have encountered about what is an event, what is a singularity, what is a group.
Right.
These kind of questions are what I'm eager to get into. So that's not a specific question for you yet, but just to give you all some context for who I am here. So, yeah.
Thanks.
I was here as a student when Heinz was here. I
Yes.
knew him, and the Biological Computing Laboratory
Yes.
was a big influence on me.
Yeah.
Martirano and Varela and Ross Ashby and
Yes.
on and on, all those people.
Yeah.
And I mean, practically going back to what the frog's eye tells the frog's
Yeah,
brain.
Yes.
So
Yes.
Warren McCullough.
Amazing.
Yeah.
The biological began
Yeah.
this whole revolution
Right.
in thinking about thought, about mind, that now you're back to biological again.
Now we're back to that, and so that's been. I brought Heinz to Mills College actually when I was head of the music department there to speak when he was living in California before I think he went back to Vienna. So second order, third order, blah blah blah.
Yeah.
On. So this is clearly something that is another emergent system.
Yes.
That we're just beginning to touch and try to think about where it might go. So the questions of how do we assign meaning to the signals? How do we create a truly feedback loop situation? And the idea of these using cochlear implants, as a way to stimulate them, is a brand new idea.
Yes.
Just recently, right? Which sounds brilliant to me, very exciting about that. And so then, of course, there are an infinite number of, the variety of ways that you could map these things is infinite. Right. So and right now it's a deterministic mapping. It's just it's a one-to-one mapping, just to see if we could do it.
Right.
And so now that we know we can do it, we can now try to figure out how do we let the order emerge without driving it.
Yes.
Don't you, right?
Yes.
And then try to understand it in a more deep way.
Yeah. Do I understand a connection here, Mattia? I'm very new and very interested in your work here. the emphasis on dynamics rather than bits.
Oh,
This is a very interesting, what I understand here to be, it sounds like some connection between David's choice to use multiple peoples at the same time for this performance, and you looking at the dynamics rather than bits. It feels like there's a important messiness to
yes,
outputs there.
Yeah, there is. I mean, you know, like let's say what we think of in terms of, you know, nowadays computing, right? It's been tremendously successful. And it's really this, you know, coming from the imagination, the math of von Neumann and these people, when they started thinking about these finite machines as a paradigm to compute, and then a machine was built to fit this paradigm.
Yes.
And this is very unintuitive from a biological perspective, because there is no system that works that way. So it turned out to work out brilliantly, right? But it has limits. And it's showing some of these limitations in really accessing these abilities, these cognitive abilities that are, you know, missing. We cannot. It seems like it's close, but they're not there, right? And perhaps that's because, as a computing paradigm, this is not, you know, it doesn't make the life easy to algorithms to be able to generate these type of traits, no? So. So the same way we don't solve massive PDEs, we're not good at that. This machine is not necessarily, perhaps not good or not, you know, the most natural way to try to encode these dynamics, and so it works by bits, right? That's also one of the reasons why it's so expensive, because you need a strong input to distinguish from the noise. But all systems out there in nature, all of us, we don't work like that. It's radically different. No, we are a dynamic system. Noise is a big thing, right? Yeah. So if you take neurons, you most likely you don't want to compute with a single neuron, because that's just noise. They are reliable only, you know, from a statistical perspective as a population, and so that perhaps connects with you know, having multiple people, because there is, you know, the emergence comes from you know, the individual parts interacting together. And but the other strong thing is that since in a neural culture in our brain, now there are so many neurons and different neurons so connected, there's no hope for us to really go and micromanage this thing. So you have to work with this concept of emergence and use it. And so that perhaps not good for exact calculations, but perhaps is good for some other type of computing that we want.
Questions are coming to mind right away, but I want to hear from David about, was there an earlier version of that project that was a single person and then you moved to the multiple, or did you start with the multiple? Am I intuiting right that the multiple comes from some of the same motivations that Mattia has here? For
the multiplicity started early with me, though. I mean, yes, there were single versions, but when I first got involved in, you know, the emergence of biofeedback in the late '60s, and, you know, the work of Neil Miller, making, you know, throwing questions into what is the autonomic nervous system, and can it be brought under some kind of individual control? And the answer is, to a certain degree, yes. And so. So it started out being individual, but I was very interested very early on in the multiplicity. And so there's a little in that brain art book. Tim Mullen and I wrote a chapter. I titled it "More Than One," which was the idea of contingent feedback. You know, in which the feedback process is somehow determined by some sort of coincident emergence of coincident phenomena among at least two or more people. So I started making biofeedback-driven pieces with at that time 2 to 4 people at a time, and not using this kind of hyperbrain thing, which we didn't know about at that time, but just creating a kind of ensemble effect. You know, and seeing where that can go. So that's been something I've worked with for quite a long time. Now this hyperbrain business is a whole other way of looking at the statistics of what goes on amongst the group. in addition to just finding coincidences. Even the piece that we performed last night was for 2 people. And initially there's a layer of sound that is attached to each individual. And then there's there is another layer of sound that maps is pretty well maps shifts of attention, which produces a certain interruption in coherent waves or auditory evoked response. And then another layer that comes from simultaneous shifts of attention, right, which is a little bit simpler than the hyperbrain thing, but still creates, and then another layer where I come out and I play with them, and then we take them away one at a time, and so on. So that's been an interest for quite some time, and yes, there's a kind of a, I think you were talking about one neuron gives you spikes and a bunch of noise, right? So, but when the group is connected, maybe in the mode of criticality, maybe the precise calculation that is done by transistors is not there, but there's the possibility of generalization. How do we make generalizations? Might be really interesting, right? That coming to make what I will call generalizations with a digital machine takes a ton of computation, right?
Right.
Massive computation, but the brain can do it like that.
Right.
So how?
Right.
Maybe we learn something
Yeah.
from this kind of thing.
Yeah, but I appreciate, Mattia, what I feel like you get me thinking about the limits you're trying to move beyond have to do with what did the von Neumann approach get us started in that we got locked into that we need to think differently from. And it sounds like my understanding of that has often been that what that got us started into was a kind of static model of what the brain is. That the von Neumann machine, once we started to think about that as thought, we were locking in a certain representation of what thought was. It has also started to influence what we think about the human. I mean, and it was limited because we left off all the other ways we could have looked at information when we started thinking about this in terms of bits.
Yeah, I mean. Yes, in a way it's true, but I mean, just to clarify, the final state machine as a computing paradigm, in principle, can generate any computation, right?
Yeah.
So it's some property of universality, which doesn't mean that you can actually do it, just theoretically, no?
Yeah.
So in principle, that also could do some of the things that we would like to do, no? Only that practically is hard to realize because maybe that's not the right model to think about it. And yes, no, because we go into this digital mode, then we also start thinking a little bit that way. But I also feel that, and of course the success has been enormous, right? So we see it every day, all the time. But I also want to say that some of these ideas of computing with biology, I mean, they go back. So these are not, it's not that all of this is brand new of the past few years. And even using neurons to try to do computations is not necessarily, it's an idea that every few years reemerges. I think we are, at least we've been successful in presenting perhaps a framework, structure frameworks of how you might actually do it. Yeah. Right, and also it's a good time because bioengineering and biology and many other technologies are much more mature than just a few years ago, right? And so yes, going back to your question, I think that influences how we think about things and digital twins and metaverse and all of these things. But there are also I think also it's not necessarily a good idea to think about as two completely separate worlds, right? Because why not having hybrid systems, right? Where these computers are very good at some tasks, you don't want to throw that away. Right. So, yeah, I mean, maybe there's gonna re-emerge at some point, another way of thinking, but yeah.
Right. I mean, one of the things that attracted me in reading about the Mind in Vitro project before coming here was that I could see in the description, the languages you used, that it was not about trying to make neurons into transistors.
Yeah, right, exactly.
So it was very attractive to think about that, and it's interesting, isn't it? Because there was this sort of mid-20th century explosion of sort of techno-optimism that came out of, I don't know, do you remember the Hickson Conference?
Mm-hmm. Yeah.
That was kind of a, linguistics, artificial intelligence, computers playing chess.
Right.
Then Hiller and compositional algorithms and music, composing algorithms and information theory, and Ted Koons and David Cranebrew wrote one of the earliest papers on information theory as a measure of structure in music, in 1950 something.
Yeah.
And that all sort of exploded, and then we had this idea that this was an endless kind of field of possibility. Well, yes, it was a field of possibility, but the way we look at artificial intelligence now is different than Newell and everybody back then. And I've recently been circled back to the work of Philip Agre. Do you remember?
I don't know.
So he was with them.
Oh.
And then split off as a real critic.
AUG.
AGRE.
He's no longer with us.
That's correct.
Yeah, this is the critical technical practice.
Critical technical practice.
Yes,
exactly.
Yes, yeah.
And and it begins to have really interesting meaning right now.
Yes.
In looking at AI, and what it isn't, and and even the notion of intelligence. We use that word. So what do we mean by that? Right. Well, yes, we have multiple intelligences and all of those sort of frameworks in which to look at it. But my joke about AI is that we're trying to make an artificial version of something that we don't know what it is. Mm-hmm. Right?
Yeah.
And even in looking for intelligence in outer space, we go to it with a preconceived model of what it is.
Yeah.
Like an anthropologist going into the jungle and having a preconceived model of social structures and completely missing what's actually going on and maybe destroying it.
Yeah, we miss what order is.
Yes.
And just as we might miss what sound is.
Right.
Yeah.
That's exactly right. So we we have to back away.
Yeah.
And there's so much there's so much work going on in music and neuroscience. Mm-hmm. We have neuroscientists who look at music and they try to find structures in the brain that process what they think music is, but they come to it with a preconceived idea of what music is. Right. Or we have musicians who are particularly interested in understanding more, or we have people in the middle, and music has turned out to be a particularly useful stimulus with which to study the brain. Yeah. So it's quite a spectrum of cognitive models that people bring to it. Yeah. So I like to see these things, become a little more deviant in their model building. Yeah.
I mean, for me, some of the stakes of this and why I wish I had spent more time in it than I did on administrative work some days is that another side of my whole my scholarship has been into nuclear proliferation and policy.
I'm a nuclear engineer.
Okay, all right, I started to look at, for example, and this is not my scholarship, other people's scholarship, the ways that those mid-century ideals of how you can look at anything as information began to be applied to international political theory as well. People like the Rand Corporation building models of diplomacy based on these same pieces. And then even early climate scientists beginning to look at the planet as if it was a von Neumann-based kind of approach of on-off that results in the environment we have, and beginning to look for only certain kind of signals to indicate what the state of the planet was that was beginning to miss some of the ones that actually are affecting us, right? So we have some ethical implications of looking at order in these certain ways, looking for a certain kind of machine and finding it, because you're only going to find what you're looking for,
right,
that we're now suffering the effects of. And so these alternate approaches, which I take your point, Mattia, I shouldn't make too big of a split, but because then I'll end up in the utopian camps of some of these cyberneticists that I do enjoy. But these alternate approaches feel really needed. I'll share one example that I forget the name of these folks that made this thing, but I want to go back and look at it. There was apparently, I think this was in Brazil, that in the 70s and 80s, the economists, the national economists, were finding trouble finding a way to model what they were looking to model using computation of any kind they could find. And so they built a water-based computer to do this, and they found that this very elaborate system of tanks and flows that they actually were doing computation with was one of the only ways to actually represent what was going on in the economy. And to me, that gets to questions of how, when you only look for bits and not dynamics, you're missing the multiple states, right? This multiple state seems like a place y'all can connect, because music is also always about multiple states.
Yeah, I think more than missing the state, because it's a finite state machine, has states, right?
Yeah.
But it's like, how you, so these are typically, and also going back a little bit with what you were saying now, that, there was a lot of hope in the 60s about AI. I mean, AI now is very powerful, but but it has clear limits, because it's a little bit static in a way that, you train it, then it takes an input and spits out an output. And, the bigger your data set and the bigger your network, the more possibilities to, interpolate where you want to be. But it's static, right? You learn the weights, and that's what it is. And then cells are not static; they're plastic, and it happens across so many scales. No, I mean, you have this all sort of mechanisms are at play, and gene regulation of all sorts, and from very very quick remodeling to remodeling that takes days and months, and how you learn a new language is not right. It takes some time. So I feel like. This ability to morph or be malleable as a system is a little bit lacking nowadays, and that has some limits. And there are many people that work still in the pure AI, deep learning domain, and they try to have networks that have some inner dynamics, and so there's a lot of effort, of course, in this. But it seems, it looks like bio is still the champion here, right? So maybe there is something to learn from there.
So to get to your experiment, because we need to be specific and honor the work, is there anything that has emerged in your conversation so far about what the RL provides as an index of what is happening in the system compared to the motile or mobile or the visual?
Oh, yeah, that's...
We've only been listening to this for 2 days.
but that's in fact not a so actually we were chatting about this. So when you listen to these two recordings, like just by listening to it, it's very clear that something has changed. It's so immediate. You perhaps don't know what the reason is, but it's just you just get it. Instead, if you look at spikes, yes, sometimes you see more spikes, it's more dense, but it's perhaps not as immediate type of, perceiving that something has changed. And then if you instead couple these systems with a motile robot, for example, then you're reducing so dramatically the number of degrees of freedom, right? Because at the end of the day, you're actuating few muscles. So maybe a few actuation patterns as opposed to, many patterns that...
A few muscles for what we can perceive.
no, I'm saying if you look
Yeah.
at it,
Yeah.
right?
Yeah,
It's a big downsampling there.
Right.
So music seems like a good. It's just intuitively a good way to, perceive, intuitively the richness of the patterns that you might generate.
Yeah.
Because it's so rich itself.
Yes.
No?
Yeah.
So yeah, that's for me. That's very interesting. I would be interested in seeing what happens when you just play, a healthy culture towards a culture. They form, they live, right? The system. So they start forming. In the beginning, they're not even a network. They're kind of baby cultures. Then they mature and they eventually die also.
Yeah.
No? So yeah, I think it would be interesting to listen to how this happens.
But I imagine, David, you want to get well beyond sonification to actually getting the idea of the sound getting back into this system.
Yeah, that's a vision.
Yeah, and for us too. I mean, the co-creative process is of course very interesting, right? The interaction.
Yeah. So who knows what we might be able to create.
Do you have y'all had much time yet to discuss even some of the differing ways you understand what a neuron is, or your different concepts of this? I think of each of your resonators, individual resonators, is kind of probably your neurons in a way, right? I mean, I'm trying to think about, you both got different models you're working from. I wonder if anything's come out there in terms of differences.
I think just possibility at this point, because this is so new.
Yeah.
But you're right, the resonators are designed not to be, they're designed to have some sort of resistance or some, yes, it's just a program, but, some sort of a little bit of indeterminacy about them that's the way I see resonant phenomenon behaving anyway. Yeah. Right? I mean, it's like this. It's not like this. Right? Yes. So that's something that has interested me in music anyway. Right. The uncertainties are become as interesting as what you can try to make deterministic. Yeah. I keep using the visual analogy of like squeezing a balloon, and it pops out here, pops out there in ways that you can't quite always control. Right. And that's really interesting. Right. Yeah. And you interact with it.
Yeah. But Mattia, are these histories of cybernetics part of your world and things you knew about, or have you? A lot of folks learn about them later after they're already doing.
Yeah, so to me, my background, I'm a nuclear engineer, right, as background. So, and then through different bifurcations, I ended up doing this. So it's not that, so to me, one famous cyberneticist, at least in the engineering community, was Valentino Breitenberg, do you know?
No, I don't. No.
So he was I think, Italian-Australian cyberneticist that was at MIT at some point as a professor, and wrote this very tiny book. It's called Vehicles. It's very easy to read.
Yeah.
I mean, you can read it in 2 hours. But to me, really, and I read this when I was a PhD. So my advisor told too. The goal was completely different, but to read this book, and I did. And so what is very interesting in this book that kind of started a little bit this line of thinking is that he thinks of these are all thought experiment, not real experiment. Right. And he imagines a very simple vehicle like a box, 2 wheels in front, 2 wheels in the back, and then some 2 sensors here. Yeah. And then he just says, if you put a light here, then this sensor will sense it a little bit stronger because it's closer, or vice versa. No? Yeah. And then if you just connect the sensing to these wheels or across, then you either go away or you either go towards the source or away, no? And so he was saying, well, this is very simple. Everyone understands that, no? But then you can start messing up a little bit more with these connections, and then he's showing how the behavior becomes more and more complex, and it starts looking like, he's scared of this type of
Yes.
sick, environment, or the vehicles loves this type of environment. And so it approaches something that we perceive as behavior, but it's purely mechanistic.
Right.
There's nothing other than connections there.
Right.
And so that is a little bit what started initially. In fact, my main interest was in this idea of mechanical intelligence, where it really is the mechanics mediates a certain type of responses that are similar to intelligent behavior. We worked on this for some time, but there are limits to that, right? At some point, you need some decision-making center somewhere, and so that's where the leap has happened into this business, basically. But going and this Valentino Breitenberg to me that was a very important readings. Now many years ago.
Yeah. I asked because we are finding all the time that we're not all drawing from the same traditions and intellectual pathways, and yet we're all in the same problems, and that's what's interesting sometimes.
It's also interesting that the people we think of are, because he comes from engineering, so that's what I know, and I don't know some of the people that you're thinking of. Many have been thinking about these ideas from many different backgrounds.
Is memory getting to be a subject for you in this? And I'm curious about this in your work as well, David, is if the memory of a performance in a hyperbrain manifestation, does the digital instrument begin to form something you would call memory of its use?
Well, I don't know that the system itself stores what's going on, but I have another instrument design direction that I haven't applied to this, but now what you're saying suggests it might be useful. In the mid-'70s, I started working with auditory event-related potentials, or evoked responses, in a system that was designed to make performance self-organizing, and look at auditory perception. And so what I developed was a feedback system in which a computer, let's say, is generating sound. Doesn't matter whether it's precomposed, random, whatever, stochastic. And I developed a very simple kind of model of perception based on the following of parameters in sound and looking for changes of rate of change in various parameters in a positive direction that the computer would use to predict where in that sound stream an evoked response might be likely to be found. Partly it was an engineering solution to you can't find an evoked response, which is a transient wave, unless you know where to look, right? So it's usually tied to the onset of a stimulus. So you can't activate the detection process and signal processing. So this was a predictive algorithm that says, this is a change in the sound that is likely to generate an evoked response. Then it goes and looks for it. If it is confirmed, if the prediction is confirmed, then the compositional algorithm increments the probability that those kinds of changes will occur again. If it's disconfirmed, it causes them to wander off in other unpredictable directions, either by stochastic processes or maybe some genetic algorithm thing.
Back to the noise.
So the result was in a performance. I made a piece called "On Being Invisible," because it was about the idea that then, as a performer, you're riding a very thin line between being an initiator of action and being a part of being a participant in the circuit, in the whole thing. which became really an interesting thing. So from that, I thought, you know, this is a model that could be very interesting just as because I'm an improviser in an instrument that we used to use the word intelligent instrument, and then that got to be a bad thing to do. People, and so we stopped that. But let's say it's not the brain, but I'm playing on a disc clavier, computer interface piano. So I use the same model as a parsing tool. So it listens to what I'm playing, and it uses the same kind of predictive algorithm to say, this is a change significant enough to then go back to the last change, gather that material and store it.
Yeah.
Do that for a while, and then it maps the ability out onto the keyboard for me to pull those things back and to transform them.
Yeah.
They bend their shapes, and then interact with them. And then there's a point where I goes into a hierarchical form builder, where it takes sets of these things, of these parsed things, and brings them back in sequence, and uses another kind of anticipation algorithm where it says, like, you know, if you hear A, you can only predict that A will be repeated. But let's say you hear A, B. Okay, so B is a change. So then it says, okay, now A, B becomes a unit. So now we'll have that, and we see where it changes, and you try to, and I can, so far, it can successfully generate maybe 2 or 3 layers. And then this form emerges, this convergence toward order and divergence and stuff like that. So that now is my instrument that I play, right? So bringing that approach back into something like the Ringing Minds piece, or maybe even what we might do, could be something to think about.
Because I don't know if we might be out of time on us, but
we are,
is is memory part of what you're heading into?
Yeah, memory is. I think in this type of system, so in a machine, memory is like, first of all, exact. You can store a huge amount of data, and it lives separate from where you compute. But in this system, compute, learning, and memory are all happening in the same place. And the way one way to think about storing some information is through the network, right? Through models upon a certain type of stimuli, and then the network is different, right? And so you might store something there, but the network also keeps changing. So then it's not this exact storing that you might think of, but you store something that evolves in time.
It's not a storage and retrieval approach. It is the network is reflective of its past activity in a way that is meaningful. And you can still restore it, recover it perhaps, but it might have changed over time. So, and that might be good. It's good. Anastasia, do we need to end? Yes. Anything else any place else you'd like to go here to wrap things up?
Oh, I think to the lab.
Okay. Well, thank you all for being here and sharing your experiment with us. This is great. Awesome.
Great.
All right.
May it keep going.
Okay.
Thank you.